Yeah, as Martin said, my name is John Orlando. I'm the CEO and co-founder at Epiq Solutions. Thrilled to be another sponsor here this year with the GNU Radio crew. We're going to be giving a talk. I'm going to be giving a talk today kind of on the shoulders of giants of our team back at our headquarters in Chicago that does a lot of work on our Sidekiq line of radio cards. In particular, we're going to be talking about something called GPUDirect and a way to be able to move 1 billion samples or more over PCI Express and into a GPU, and some of the research we've been doing in that space and kind of the direction we're headed. So quick company background about us. We are celebrating our 10th year being in business this year, delivering very, very small form factor software-defined radio cards to a whole host of different customers and use cases. If you're familiar with our Sidekiq cards, they come in mini PCIe and M.2 and a whole bunch of other flavors. Stop by our booth if you want to take a peek at them, see some of them operational. We've got a team of 40 folks and growing. I'll put my plug here and at the end for we're hiring, so if you like to make cool radio things, come talk to us. But let's get right into it. Standard SDR problem has three main components, right? At a very high level, people have some sort of antenna, some sort of RF front end, and data converter. I'm going to move this up a little bit to make sure it's getting it. And a compute element. There's lots of debates around what the right way is to do this. I'm not going to get into the religious debates around this. What we're going to focus on primarily is how data moves from that data converter into your compute element, and in some sense, kind of which compute elements make sense to be using for different kinds of applications. So that's the super 10,000-foot view. We've been spending a lot of time looking at, as the number of channels increase, as the bandwidth of these channels increase, we have a problem that needs to be solved. And that problem is nothing is getting easier in this world of how many samples, how much data do you need to be able to consume. Back in the days of old school cellular 2G GSM, things were easy. You can do it, you can gobble up a couple of megabytes per second on almost anything. As we went to 3G and 4G and then variants of 802.11, and now we've got 5G NR, kind of at the state of affairs, you have 400 megahertz wide channels, you have multiple antennas, you've got a veritable crap load of data that you have to deal with. So when we think about compute elements, compute options for this kind of data flow, you really have three cases people consider typically, right? Everybody knows about doing this on GPPs and a CPU. You also have GPUs and you also have FPGAs. I have the kind of original DSP, like not as in digital signal processing, but digital signal processor chips, also as an option up there, but primarily I would suspect 90% of the people in this room are using one of those three main categories for their signal processing. And if we're pragmatic about how we actually want to accomplish tasks like building radios, there's a whole lot of software engineers out in the world. There is a smaller number of software engineers that understand signal processing. There is an even smaller number of FPGA engineers. And then you have this little itty bitty sliver of folks that can do FPGA signal processing at the end of the day. And that's a log scale. And this is not actual data. This is completely made up just after being in the industry for about 20 years. So when we think about what we could do to be able to take advantage of the software folks we have in the universe and solve signal processing problems, the right spot to kind of focus on sits in this middle category. As a company, we do lots in FPGAs, but it is incredibly hard to recruit and find good talent that are FPGA jockeys and signal processing jockeys, and I see heads nodding, so good. I'm glad to hear we're not the only ones doing that. So this is going to be a talk kind of about using GPUs and what they can enable, but not so much on the, hey, I'm going to go do a bunch of signal processing kernels in my GPU. It's all about how can you get data into the GPU in the most effective manner possible. The Eureka Moment here is kind of tongue-in-cheek, right? At the end of the day, people have been doing work with GPUs and signal processing for years. There was some work published as it relates to GNU Radio back in 2011 for being able to use a GPU for doing the computational portion of a signal processing block. But you had to get the data into the CPU, and then the CPU had to shuttle it down to the GPU, and then you had to get it back. And if you're like our team, you've probably found that that shuttling activity can seriously kill any benefit you have by using a GPU. There are cases where that's not necessarily the way it goes, but commonly that is the case. So the classic architecture here, let's see, does this, yeah, well, so the classic architecture here, if I can, there we go, perfect. You'll have your analog signal coming in, you'll go through a front end into your data converters. You will have some form of digitized interface going into your FPGA. Maybe that's JZ204, maybe that's something else. That FPGA will typically package up those samples, move them typically over PCI Express or some other interface into a host CPU, where they will be DMA'd direct memory access into system RAM. And then to get them to the CPU, to get them down to a GPU for processing, the CPU will have to pull them out and push them back over PCI Express, most typically, and down to a GPU. So this is kind of the classic architecture for how a lot of systems work when you're talking about having a GPU in the mix. Our question was, can we do better? Can we increase throughput? If we can, by how much? We were interested in understanding kind of the bounding boxes here. So with that, I'm going to talk a little bit about this thing called GPUDirect from Nvidia. So what is GPUDirect? It was developed by Nvidia back in 2013. Their basic premise was we want to have a mechanism that lets you move data, regardless of what kind of data it is, into a GPU over PCI Express without having to have the CPU play any significant role in that process. So Nvidia rolled this out. It's kind of gotten some traction over the course of time, but not a ton of press. The idea here is there's kind of a software driver that allows PCIe devices to target DMA transactions directly into the GPU memory through the PCI Express root complex without ever having to go up to the CPU and back down. If you're familiar with doing NVIDIA GPU-based programming, CUDA is a typical way you would be building computational kernels down on the GPU. And if you can kind of make all of this work, at the end of the day, the CPU kind of sets things up and gets the hell out of the way, which is nice. In theory, it's more efficient. You should be able to get more throughput. You should be able to use fewer CPU cycles in the mix. You should be able to lower your system power consumption because the CPU isn't doing as much, and generally winning, which we like. So it would take the architecture from this to this, where you are doing this very efficient path going from the radio front end into the FPGA, a brief moment inside the CPU, but only into the root complex, and then back down to the GPU to let the GPU do the thing that it's good at in crunching on the samples. So what do you need to be able to accomplish this? Well, you need a couple things. First and foremost, you need a radio that knows how to emit samples over PCI Express. We happen to make radios that emit samples over PCI Express. The one most appropriate here, our Sidekiq X4 card, which is a VIDA 57 compliant FPGA mezzanine card. It has two of Analog Devices ADRV 9009 RFICs, which is their most recent RFIC they've introduced into the market. So on this one card, you get a 4x4 MIMO capability that gives you either 4 200 megahertz wide channels or up to 800 megahertz wide instantaneous bandwidth that you can consume. It's got integrated pre-select filters supported by our standard API. If you want more details, come find us. The idea here, though, is you would take that card, plug it into some sort of carrier, whether it's a commercial carrier for a standard PCI Express slot, or into something like a 3U VPX card for more ruggedized deployments. The combination of the X4 card and one of the two carriers then goes into a host system, and voila, you've got gobs of bandwidth going over PCI Express into some host system to then be processed. So as a backdrop, that kind of sets the stage. We have a bunch of different other radio cards. This is a bit of an eyesore, but all the ones along the top in our Sidekiq family have PCI Express support. The slides will be available if you're into the details. You can check them out later. The other thing you need is the compute element side, right? You need a GPU in the mix, and you need some sort of CPU to kind of set things up. The two main systems that we were looking at here was a standard x86 motherboard with an Nvidia Quadro P2000 graphics card plugged into it, and a Core i7 CPU, as well as an Nvidia Xavier platform, which is their most recent kind of low-power GPU-CPU combination. So both of these platforms end up being fairly good for doing some evaluation of GPUDirect, so we decided that kind of made sense. One other point to note here, again, it is necessary for GPUDirect to work to have the GPU and the radio on the same PCI Express root complex. That's taken care of you implicitly in the Nvidia Xavier platform by design. So roughly how it works, if you're familiar with DMA, it's almost exactly like you would expect it to be. The CPU is responsible for pinning down a block of memory inside of the GPU and kind of reserving it. The CPU is responsible for telling the FPGA and the radio card, hey, here's this physical address space in the GPU that I want you to be able to target your DMA transactions to. CPU gets the hell out of the way, and the FPGA can then start dumping data over DMA directly into the GPU, while the CPU, for the most part, sits back. GPU crunches the data like a champ, and then you go to step 4, and you can kind of repeat this loop. So our question was, great, theory's awesome. Does it work? We set out to figure out what kind of difference it actually makes. So we went through and updated our current PCI Express DMA driver that works with our Sidekiq cards to support GPUDirect. We built 2 hardware platforms, exactly the ones I described to you before, i.e. a commercial off-the-shelf gigabyte motherboard, a PCIe carrier card with our radio on it, and then a Quadro GPU card from Nvidia, as well as an Xavier-based platform to be able to see how well this works. Both of these run Linux. GPUDirect does not work in Windows currently. There's a little bit of talk about trying to make that happen, but for the most part, this is all Linux all the time, and we wanted to see how it would go. So we had 2 test scenarios, right? The old way, we're going to go FPGA to CPU to RAM to CPU to GPU. And then the new way, we're going to go FPGA to GPU. And just for kicks, we'll do a simple computational kernel in the GPU. Again, this is not about is the GPU efficient at processing signals. This is all about understanding the throughput benefit of getting data over GPUDirect versus using a more traditional method. So the test results. We went through and set up our first system, platform number 1, and we did the old way, where you have to go all the way up to the CPU and come back down. And we were measuring just north of 1,700 megabytes per second. Didn't seem too bad, reasonable amount of data going through. And then we got all excited and we fired up the GPUDirect way, and it was a whopping 1,733 megabytes per second for exactly, you guessed it, 1% performance improvement. So we sat there for a while and we said, that doesn't seem quite right. What could we be doing wrong here? Either GPUDirect sucks or there's something else about it that we're missing. It turns out there was something else about it that we were missing. There's a bunch of head scratching. We stared at the platform a little bit. We ran some more tests, and of course you got to go check the hardware at the end of the day to really figure out what's going on. So let's look at this. We originally had this loaded up with a PCI Express Gen 2 by 4 DMA engine, which means we have 4 lanes of PCI Express running at Gen 2 speeds. If we do a little bit of math, each Gen 2 PCI Express lane gives you 5 gigabits per second. We have 4 lanes, so we get 20 gigabits per second through that path. There is 8B, 10B coding on the lane, so you actually reduce that by 20% down to 16 gigabits per second. A real-world PCI bus utilization to kind of expect is maybe 85% efficient or so. And does anybody want to guess if you divide 13.6 by 8 bits, how many megabytes per second that is? That is exactly almost 1,700 megabytes per second. So what does this mean? It means that we effectively had the PCI Express bus as the limiting factor in this first test scenario. So we said, great, for these cases where you're in this range, there actually isn't any throughput benefit to using GPUDirect unless you want to have your CPU restored, CPU set aside to do some additional processing. The path going FPGA to CPU to RAM, back to the CPU, back down to the GPU, or going right from FPGA to GPU, same throughput that you can achieve. So what now? Well, we said, let's take another look at this. Try take 2. What if we go PCI Express Gen 3, we bump it up to 8 lanes, and we see what kind of difference that makes. The motherboard actually supports up to Gen 3 by 16, but we wanted to go with by 8. If you're not a PCI Express jockey, Gen 3 gets you to 8 gigabits per second per lane. We have 8 lanes, so we've got 64 gigabits per second of throughput. It uses a different line coding. We have 128B, 130B, which actually means we only drop down the overall throughput to about 63 gigabits per second. It should be plenty, right? And we redo the tests, and we hope that sanity is restored. So take 2, drum roll please, test 1 the old way. We're now up to 3.2 gigabytes per second. Not too bad. Definite improvement that we see. And of course, the GPUDirect way, that's what we're looking for. So now we're at 4.7, just under 4.7 gigabytes per second. There's about a net 45% throughput improvement in being able to move data from the radio into the GPU compared to what I would consider the old standard way of not using GPUDirect. So that's actually pretty important. From our view, sanity is kind of restored here. We were happy to see that improvement. We weren't exactly sure what to expect in doing these tests. And more importantly, if I go to the next, there we go. More importantly, we wanted to see what it looked like when we went to the Xavier platform to see what it was able to do. So we did test one the old way, up to the CPU and back down. A little bit lower, not unexpected. It's lower power. Xavier has ARM cores versus x86. We were seeing just north of 2 gigabytes per second. And then we did the GPUDirect way. And it turns out it is almost an identical percentage improvement throughput for Xavier compared to the x86. Total is still lower, but in terms of percentage improvement, 46% versus 45%. So we were pretty happy to see that those numbers seem to line up with things here. So the answer here is yes, Virginia, you can move more than 1 billion samples per second over PCI Express directly into a GPU using GPUDirect and RDMA. 4677 megabytes per second equates to about 1.17 gigasamples per second, assuming you have 16-bit I, 16-bit Q. That is enough to digitize 1 gigahertz of RF spectrum and get it into a GPU without the CPU having to be substantially involved. As best we can tell, SDRs based on PCI Express radios give you the most efficient, scalable, low-power transport way out there on the market today in terms of being able to extend to these bandwidths and these channel counts that are going to matter. And GPUDirect is kind of a natural fit in this space. But that question of does it matter is pretty important. Because if you only care about 10 megahertz of spectrum or 20 megahertz of spectrum, it probably makes no difference to you, unless you have a boatload of processing you want to do in the GPU to kind of push things forward. But if you care about single channel bandwidths that are like in these gigahertz plus ranges, if you care about MIMO 2x2, 4x4, more than that, where each channel bandwidth is going to be hundreds of megahertz potentially, or if you just want to keep your CPU cycles for something else, or do your GPU jockey and that's where you want to do your processing, then yes, GPUDirect does matter, and it kind of matters big time in terms of the overall throughput. It may be the only way to get the results desired that you want. The other nice thing that working with GPUs, not specific to GPUDirect, but having GPUs in the mix gives you a fairly nice path for being able to interconnect processing nodes together. I long for the day when there is a way to kind of have a flow graph and properly deploy the signal processing across all these different nodes, whether with the work that RFNOC is doing with FPGAs, I think is right in line with this and kind of parallel. Doing something similar with GPUs from a higher level thing would be super awesome. Nvidia seems to be pushing pretty hard in some of these spaces for how to scale this, and especially as the bandwidths go up and up, I think it'll be a big deal. So we'll be pushing GPUDirect support in libsidekiq coming fourth quarter of 2019. The two initial versions, the two initial radios that are going to kind of get most of the focus is going to be Sidekiq X4, this one that has 4 200 meg wide channels where you can look at an aggregate of 800 megahertz instantaneously. That makes the most sense and probably where the most benefit would be realized. As a second tier, our Sidekiq Stretch that a little bit has been talked about through the lightning talks earlier. It's our more recent offering, single receive, single transmit in a 22 by 80 M.2 card form factor. Only 61.44 megasamples per second. But even at those rates, you could seriously, you could potentially peg a CPU if you were really trying to crunch through all that data. So there still may be some benefit, even with a narrower bandwidth, in being able to make this work with GPU. Finally, some areas for exploration. You're still doing DMA descriptor management, so the CPU is still involved a little bit here. There's some back and forth on the best ways to handle that. Other things I'd say of question, the optimal data transport size. GPUs like big blocks of data. Right now, we're still kind of working with what's standard in PCI Express DMA blocks, which is 4K bytes. Probably the biggest one is how the metadata for IQ streams get handled. When we're transporting our data, typically we have a header that is precedes the IQ with things like timestamps and gain values, things specific to the radio. If you want to check to see if you have timestamp gaps or you want to assess the gain, the GPU will need to be the thing that actually does that. And possibly the way around this is just to kind of give it raw IQ data and worry about the metadata kind of out of band and assume that the GPU will be able to consume things and keep up with it. And then, of course, integration with GPU frameworks or something from the MITRE folks called Photon that is hopefully going to get some more kind of lighted day out there in terms of what's going on with that. This could be a great fit for that. And last but not least, this is all very NVIDIA specific and CUDA specific. If you are an OpenCL guy or girl and interested in doing work in that space, there may be some ways to make it work. There's something called direct GMA or bus addressable memory that could provide a lot of the same advantages. If you Google around OpenCL and PCI Express and DMA, There's not a whole ton out there. The last active work that we could find was several years back, so we need to do some more exploring to see if we're just not, our Google foo is not sufficiently strong, or if there are really people interested in doing this. The exact same ideas should work and should be viable. So I'd like to give a quick shout out to some of the MITRE folks that helped fund a portion of this development work, as well to our Sidekiq team that did the heavy lifting, and to all our customers that continue to use our Sidekiq cards and deploy them all over the world. And I said at the beginning of the talk that I would be revisiting this one more time. If you're at the top of your game and you like building hardware and software and SDR is your thing, we are hiring and would love to come talk. We've got a booth over in the center here, and or send us an email at jobs@Epiq Solutions. So with that, that is everything we got.
Time for questions.
Hey, John, great talk.
Thanks.
So you kind of mentioned that when things evened out, you're like, oh, it doesn't really matter for certain cases, one or the other. Did you do any power measurements? Because I'm wondering if it saves you a significant amount of power, even if it gives you the same performance.
Yeah, it will absolutely save you power. And the two things we want to spend a little bit more time exploring is how much power does it really end up saving you? Can the CPU drop to a lower power state within, before it has to do some descriptor management? What does that equate to? And then we gave kind of a pre-briefing to some customers earlier this morning on this, and they were asking about, like memory bandwidth. Like how much more do they really have free on the CPU for doing other things while the GPU is chunking away? So there are areas for exploration. I'm pretty confident that there are some non-trivial savings there. We don't have them quantified yet, though.
Were you able to succeed in this endeavor with open information, or did you have to sign non-disclosure agreements?
We did not have to sign any NDAs. We started with what Nvidia publicly has published. If you Google GPUDirect, you'll see some of the pictures I had up there and a bunch of information, and we're able to make it go.
So how often does the CPU have to interfere to update, inform the GPU that, hey, that DMA transfer is complete, you can
That is an excellent question. Yeah, and that's one of the areas right now where getting to the larger transport blocks will make a difference. Right now, you're basically saying, hey, every time we have completed some number of DMA transactions, we need to be able to know, and we need to be able to signal and say, all right, you need to be able to, the GPU is ready to go, right? Because that's still piece. The beauty of DMA is that nothing has to know about it. Something has to know about it. Something has to kind of keep pace with it. We've looked at a couple of things. We've looked at a couple ways to try to help, I guess, reduce that load. And there's a balance between how much data you're willing to potentially miss and how often you really want to be able to inform the GPU that, like, you're good, you can take the next block here and go with it. So, so there's that balance is definitely there, and it's going to end up being very application specific. Yep.
That's incredibly impressive, but I would really like a long piece of fiber between my antennas and my SDR and my ugly data processing, which I prefer to have in a Faraday cage far away. How can you integrate this with a 100 gig link or something in between?
So there is work that we've seen with folks trying to figure out how to plumb 10 gig, 40 gig, 100 gig into GPUDirect, right? And you end up playing some similar games. In other words, imagine your network, your kernel network stack where you're trying to allocate buffers that are in the GPU. So normally when data's flowing in, you're trying to feed it in from your network card. You're actually trying to push it down to the GPU. The little bit we looked at it, it felt very clunky. Now there's no doubt about it, Ethernet is everywhere, like networking is the future. I think there is a argument to say that it's worth trying to figure out how you can do that in a more effective way. From our view, it does not feel like the most effective, efficient way to actually get data into the. This is exactly what PCI Express was meant for, right? I would love to see people that are moving PCI Express over longer cables, but I think that's a kind of a long haul as well. The other piece that we're really trying to push for is you have to put the processing near the antenna, right? The other separation here is just to say, what can we do to make that work, or to figure out how that topology is a little bit better suited to the problems and not necessarily having to dump everything back.
Very impressive. I'm just curious, did you guys ever try to saturate the entire PCI bus? Go big.
Yeah, also great question. This was as far as we took it in the time that we had available to it. What we suspect is that we're probably running into how fast we're running the FPGA fabric that's interfacing to the DMA. Like there's going to be this point where that's running at a couple hundred megahertz or whatever it is, and that is going to be the thing that's actually driving it. That logic is certainly capable of going faster on the FPGA side and the DMA engine side. It just takes more. We're getting into that zone where we're going to have to be real careful to be able to scale that up to say 300 megahertz or 400 megahertz logic across kind of parallel buses before it hits the SerDes for actually getting over PCI Express.
Okay, but
Anything
I think there is also no more questions. So with that, well,
Awesome.
thank you again
Yep, thanks, guys.
for talking and for sponsoring.